EG-121, Transportation Engineering and Surveying, Video Lecture 8E, Transition Curves. Good, so let's look at a car travelling at a constant speed around the following track, and we've given it two circular curves. So in the last section of the course, we looked at designing circular curves. Car goes in a straight section, circular curve, straight section, circular curve. What is the flaw in using a circular curve to join these two straight sections of road? Have a think. On the straight section, our acceleration is 0 meters per second squared, whereas on the circular curve, our linear acceleration is v squared over r meters per second squared. So we're going from 0 acceleration to v squared over r acceleration over an instant. What would the acceleration versus time graph look like for this track? It would look something like this. So we're moving from no acceleration instantly to what might be quite a high acceleration if the curvature was high, back to 0, back to high, back to 0, back to high, back to 0. Is this going to be comfortable for the driver? So let's redraw that graph. And let's talk about it in terms of derivatives of distance. So distance d, measured in meters. The first derivative of the distance is velocity, which is our rate of change of distance. The second derivative of distance is the rate of change of velocity. And what you probably haven't come across before is the jerk, sometimes called the jolt, with the symbol J, which is our third derivative of distance, which is the rate of change of acceleration. And that is what we can express as being quite uncomfortable here. The flaw in using a circular curve to join two straight sections of the road is it's not the acceleration itself that's dangerous, it's the change in acceleration. It's this jerk that can be uncomfortable. And as I said, for high curvatures it can also be dangerous because it can throw a vehicle off track. It's more important for trains than it is for cars as well, because trains tend to travel at fairly constant velocities. So we use something called transition curves, which connect the straight sections of the road to the curved sections of the road by varying the jerk. Same car, it's now going to travel around the yellow track. We've got a straight section, we've got a circular curve, but they're connected using a transition curve in the middle here. So what we end up with is a more gradual increase in curvature, travel around the circular curve, and then a decrease in curvature. Rather than having a situation where the jerk is very high, we can now modify that so that the driver experiences a much smoother jerk, a much smoother jolt, and not that rapid change in acceleration. So what we have here is our circular curve. We've had to shift it by an amount s, and we're cutting it short, and then connecting that circular curve to the straight lines using these transition curves in green. Now the transition curve is in this case based on an Euler spiral, which is an infinite curve whose curvature changes linearly with its curve length. So you'll see these spoken about as spirals, clothoids, or conic spirals. In effect, what we do for the transition curve, we select a portion of the Euler spiral, and which portion will depend on how big our circular curve is, how big the transition curve needs to be. But what it allows us to do is connect a straight piece of road to a curved piece of road and allow that to be much more smooth. So we've got our circular curve, our transition curve. Back to this diagram. We use 3 design formulae for transition curves. The variables involved are S. S is the shift, which is this distance change for the circular curve to accommodate the transition curve. L is the length of the transition curve. R is the radius of the circular curve. And V is the design speed. C is the rate of change of radial acceleration, which is normally given, so that I will tell you what the rate of change to use is. Look at some geometry. We want to work out IB. B is the midpoint of the transition. Okay. So the distance IB must be equal to R plus S, because this is the distance S, and that gives us what would have been our original circular curve. So it's actually a modified radius, original radius. Multiplied by tan theta over 2, which you should recognise as the equation for the tangent length. BT is equal to L over 2, because B is halfway through the transition, therefore BT must be L over 2. IT is the distance from the intersection point to the first tangent point. That is going to be equal to IB plus BT, which is what this expression here is. If we assume that the Euler spiral, so this transition curve here, we've got a straight line, and then we're joining up to our curved line up here, circular curve's going to be over here somewhere. Then we can assume a cubic parabola for the transition curve itself. So we want the variation x to be equal to y cubed over 6RL. When y is at its maximum value L, what does the expression become? It'll be x is equal to L cubed over 6RL. That cancels down, and we end up with x is equal to L squared over 6R. Okay, so let's do an example. We've got a transition curve which is required for an A2 road, 5% super elevation with a design speed of 85 km per hour. The bearings of the 2 straight roads to be joined are 17 degrees and 59 degrees. So what I'm referring to there are the whole circle bearings from north. You can assume north is north here, straight up here. So this angle here, 17 degrees. Switch that slightly. And this angle here is 59 degrees. You should be able to see that that can give us our intersection angle. So our intersection angle is going to be 59 degrees minus 17 degrees, which is 42 degrees. 5% sort of relation, design speed 85 km per hour. We are assuming a C value of 0.3 meters per second cubed for C. So what we've got here, let's go for green. We've got a straight road here. We've got a straight road here. They're going to be connected by a circular curve, but that circular curve will connect to the straight sections by a transition curve section. And that's what we're going to design at the minute. To do that, we need to find the transition length, the shift, and we've got equations for both of those. The length along the tangent from the intersection point to the start of the transition IT. Okay. So we've got our transition points T1, T2. We've then got a second transition pair of points. Let's call them T3, T4, between the circular curve and the transition curve. We need to work out the equation of the line that dictates that spiral, that cubic parabola, and the coordinates of the point at which the transition becomes a circular arc of the radius r. It should be these points here. To set out transition curves, we often use the offset method, so rather than using a radial method where you set up the total station from a single point and you use deflection angles, which we've done in setting out of circular curves, you will generate a setting out table based on a baseline. In this case, it would normally be the tangent line here. So you measure a certain distance, y, and it will give you an offset perpendicular distance, x, to plot out where that transition curve goes. So, transition length, we've got equations, plug them in. We can work out from our design speed table, we've got a design speed of 85 kilometers per hour, 5% super elevation, minimum radius of curvature is 510. Everything else we know. Now, the units of these make notes because v is in kilometers per hour, whereas radius is in meters. So they are, that's the reason for these conversion factors. So put that in. L is 86.03 meters. We need to check that against the maximum permitted transition length, which is calculated as 110.6. So we're okay here, because we come in under that. The shift we calculate using this equation. Once again, we've got the length now. R24 is part of the conversion, so our shift is 0.605, and that is the distance along which the circular curve has been shifted to accommodate the transition curve. The length of IT is the distance from the intersection point to that first tangent point. Putting all the values, we've worked out theta, we know L, we know R, we know S. So that's 239.015 meters. And that's then enough to work out the form of the transition spiral. So the equation is this for a cubic parabola, as long as you've got the radius and the transition curve length. Put those numbers in. This allows us to generate the offset table for setting out. If we can have a, let's say this is our baseline, so we've got T going up to I, and then going off somewhere there. If you read this tangent line as being a baseline, reading Y, so at the start of, at the tangent point there it's 0, let's take 10 metre intervals, 10, 20, 30, 40, etc. This equation then allows us to find out the equivalent perpendicular offset distance of this spiral. So at 0 it's going to be 0. At 10 it might be a small offset distance. At 2 it might be slightly more, at 3 it might be slightly more, and at 4 it might be slightly more. But what we're getting each time is that x distance here, which is the offset distance from that perpendicular y baseline. We can find the point at which the circular curve commences. It's the same formula. All we've done is set y is equal to L. Therefore, L cancels from the base, so what you have is x is equal to y squared, L squared, sorry. L squared over 6R. And that gives us an offset distance, so we go all the way up to y is equal to L, and then that offset distance, that final offset distance there, is 2.419 meters. That allows us to plot our transition curve. And at this point, the circular curve will then start. Good, let's use that equation to work out the table to offset it. Assume 10-metre intervals. You should probably have an extra one at the top going 0, 0. But so from 0 down here, we've got 10. The offset distance is tiny. It's 4 millimetres at 20 metres from the tangent point. The offset distance is 3 centimetres. At 30, it's 10 centimetres. At 40, it's 243 mil. So it's getting increasing, and each step it increases proportionally more, and that's because the spiral is increasing. Its increasing curvature, and its maximum curvature will be the curvature of a circular curve, so that transition is smooth. So this is all you need to go out on site and calculate and set out a transition curve. You can now do transition curves and circular curves. Have a look at the self-study examples. The end of term test will cover all of the material that is covered in the self-study, so you should always be keeping up to date with those, making sure you're on top of that. It's going to come up pretty quickly, it's only a couple of weeks away now.